this project and this year. Well, that 5% still depends on where that
There's no, I mean, petitioning just means that if you're sick, then you can do it. Like, it's not like I don't want to do it. Like, that's not an option.
Thank you.
Yeah. But, sorry. So, yeah, like, if you're sick, there's the guys, you got to explain that. Like, it's not like, I mean, for this course, like, the option, like, I'm kind of like, not to, like, yeah. One, one, one. It's just we got it, Terry. Yeah, I mean, there's lots here. All right, hi everyone. Hello. So is there something to or something? There's like fewer people than usual. There is a quiz. You should go do the quiz. Don't tell your friend. Well, tell your friend. So okay, all right. Just to remind you, and like I'm cognizant of the fact that there's lots of things due. But just to remind you, the Pong is due. I think whatever it said, I think December 4th. So like to win the tournament, it does require, extra work, but you get to win the tournament, you get the prize, you get bonus marks, you get the respect of your fellow students, and stuff like that. To just get the half point towards your course grade, it's honestly not a lot. Like, you need to sit down and figure it out, but I think most people can do it like in a couple hours tops. So if you're interested in half a point towards your course grade, you should try it. Other than that, the marks for the midterm have now been like calculated and put on purpose. That's not including all the regrade requests. There is like, think about like 7 or 8 that still have not been handled yet. So the way the regrade requests work is so first of all, like 2 or 3 TAs or 1 sometimes mark each question so that it's consistent, so that roughly the same person or like the same team of people do the grading. So your request goes to the TA. If you're still kind of disagree with the TA, you can appeal to me. So just by email, you can kind of send me in. So I get the emails from Gradescope as well, but usually I assume that everything's fine. So if you feel like there is an issue, just email me and I will take a look. So the quizzes, like obviously at this point, we're not doing like super substantive quizzes. Like if you did the quiz, you got full points for each quiz. Yes. Is it not posted again? It's like literally there. It says published. There's nobody sees the quiz. No? Yeah. Okay, I don't know what's going on. So, okay. Yeah, okay. Yeah, you got graded on it, but everyone got, no, I think it wasn't just, I don't think everyone got 1.67. I think it wasn't just the survey, but everyone gets kind of, if you did the quiz at all, you get full points for the quiz. Okay, all right. So while you're contemplating what to answer on this week, or this lecture's quiz, I guess, I want to talk a little bit more about and complexity analysis. And what we're going to start doing today is sorting algorithms. So I'm going to present them in an order that might be a little bit unnatural, just because I want to make sure that you get an example that's useful for project 3 as soon as possible. So we're going to start with this kind of setting. So let's say that I want to sort a list of integers, and they have to be integers. And let's say that they happen to know that doing insertion operations into a dictionary is constant time. So what I mean by that is saying something like D at K is 5, or something like D at K is 10, or something like K and D. All of those take constant time. So how exactly to make a dictionary that works like that, we'll talk about in ESC180. For now, I just want to say, okay, this might seem extremely natural, like what else could it be? But it's not, right? So imagine a situation that's kind of like this. So imagine that you want to say, like, the list is whatever 5, 6, 7, 8, 9, 10, and you want to check like something like this is 8 in L. That is not constant time, right? Just, like just common sense. If you need to know whether 8 is in L, well, you need to look through all the elements of the list L in order to figure out whether 8 is in there. So in fact, it's O of length of L. Right? Because in the worst case, what do you need to do? Well, you need to check, is 5 equal to 8, is 6 equal to 8, is 7 equal to 8, and so on. In this case, the list happens to be sorted. So as we saw, you can do binary search in order to do it quicker, but I never said it's sorted, right? So maybe it's like this. So in the worst case, that would be O of length of L. However, with dictionaries, checking whether K is in the dictionary D as a key, it can be made to be constant time. We'll see how in ESC180. So there's some math and stuff. So, okay. So back to, I want to sort this list of integers. So how do we do it? So now we don't do it, but it used to be that we would mark exams on paper, and that's like 300 exams. And in order to return them, you can't just like throw them on the floor like that, because then the students would not be able to find the exams. You want to sort them so that the student can do something like binary search in order to find their exam, right? If it's alphabetically sorted, then you can find it. So how do you sort exams? Well, like it might be that it's a little bit of an open research question, but one thing that works is you just say, okay, we'll have a pile of A's, and then a pile of B's, a pile of C's, a pile of D's, and so on. And first, we'll just kind of separate the exams out into piles of last name begins with A, with B, with C, and so on. And then inside of that, it's not that difficult to sort because there is a lot fewer. For letters for which there is lots of last names that start with those letters, you might like to try to iterate that again. So just say kind of whatever, like Z up to like ZH and then beyond ZH or something like that. All right. So what I'm going to do here is kind of say, okay, we'll try to do the same kind of method for a bunch of integers. So there's going to be a little bit of an adjustment here. So what I'm going to say is the idea is keep track of how many fives. And keep track of how many sixes. And so on. And once you know that, then you can figure out, okay, now I know what to do, right? Because now if I know how many fives, well, I'll just like, okay, 3 5s, okay, it starts with 5 5 5s. And then I have 1 6, well, just put in the 6. I have 3 7s, 7 7 7, and so on. All right. So this idea is called counting sort. And again, the idea is like this. I'm going to say, I'm going to start with my array that were list, that's counts. And I'm going to say this many zeros, this many ones, this many threes, this many fours, this many fives. Let's say that the list is like 5 1 2 1 0. So what does it mean? It means that I have 1 5, and I have 2 1s, and I have 1 2, and I have 1 0. And now that I have the counts, I can have the sorted version of the list, right? So the sorted version of the list would be, well, I have 1 0, and I have 2 1s, and I have 1 2, and I have 1 5, and I'm done. Make sense? So, and the reason it's called, so the algorithm is called counting sort usually, is that what you're doing here is you're counting how many elements you have in the input list. And then based on that, you're outputting the outputting the sorted version. So, okay. So how should we do it? Well, so I'll first make a few assumptions just kind of to simplify matters. So I'll say that, assume that L is a list of integers. And I'm going to say, assume all integers are greater or equal than 0. And what I'm going to do now is I'm going to have my counts list. So initially the counts should be all zeros. So the way I'll do it is I'll say counts is 0 times max of L plus 1. Right? So the idea here is counts at 0 is the number of zeros. And counts at 1 is the number of ones. Initially it's 0, but then we'll update it as we go. And then counts at max of L is the number of max of L's. And the reason it's plus 1 is because I want to be able to go up to max of L. Make sense? So, all right. So now what I'm going to do is I'm going to say for E and L, counts E plus equals 1. So I go through the list. So I say counts at 5 plus equals 1, counts at 1 plus equals 1, counts at 2 plus equals 1, and so on. Bit of complaint. worked for a couple of minutes. All right. So now I have my counts. So at this point, I'm ready to actually make my result list. So initially it's going to be empty. And then I need to extend it with counts 0 zeros and counts 1 ones and counts 2 twos and so on. So, okay. So I'll say for num in range length counts. And I'll extend it with this many nums, right? So I'm saying, make me a list of, for example, I have 1 0, so make me a list of zeros of 1 0, and then make me a list of 2 ones, and then extend the result with those. And once I'm done, I'll return the result. So one thing here is I need to rely on a particular behavior. So if I say like 12 times 0, that's going to be the empty list because it's like repeat 12 0 times. Well, that's like don't repeat 12. So that's going to be the empty list. And if you extend with the empty list, result just doesn't change. Make sense? Questions? Yes. So we start, so we want to set up this list counts where initially we haven't seen any zeros, any ones, any twos, any max of L's either. So it's like 0, so max of L plus 1 zeros, right? And this is what it is. So initially this is 0 and this is 0 and this is 0. And then we go through the list and we update counts at E by 1 every time we see the number E. And now that we have the counts, we just build up the result. Make sense? So, okay. So that's like that. What's the complexity of this? So I'll write it out the once. So height asymptotic bound on the worst case runtime complexity. That's kind of a lot of legalese for just saying what's the runtime going to be proportional to. So we got to go line by line. And here you can't kind of, well, like maybe you can kind of eyeball it and be correct, but that would be an accident. So you need to actually go line by line and do something like count the operations. So this line, what is that? Oops. So this line, what is that going to take up? Well, we have max of L. Max of L, like if you think about how do I compute max of L? Well, I have to go through the list L and update the current maximum. But it's nothing more than that. So max of L is going to take a runtime, just computing that is going to take a runtime that's proportional to the length of L. And then what's the runtime here? Anyone? Like for the entire thing. Let me put it a different way. What would make the runtime of this really, really large? Yeah.
I guess if you had a large max L.
Yeah. Yeah, you need max of L plus 1, in fact, zeros, right? And then max of L can be very, very large, like integers can get pretty large. So that could potentially take a very long time if you have to fill your entire memory with kind of zeros. Right? But how much is it gonna take? And the answer is, well, it depends on how picky you are, but basically something that's proportional to max of L. So that means that the runtime for the entire thing is gonna be K1 times length of L. So if we can think about it in terms of operations, so some number of operations that's proportional to the length of L, that's to compute max of L. That is my grandma. It is. I'll say hi. So that's going to be proportional to that. And then in addition, we need to actually put max of L plus 1 zeros into memory. And that's going to be something that's proportional to max of L. So to say something that's proportional to max of L, I'm going to say it's equal to K2 times max of L. And I'll say maybe so operations. So I don't need to exactly say what K1 and K2 are. The idea is, well, max of L takes a time that's proportional to length of L. So it's going to be K1 times length of L. For some K1, I don't need to specify what K1 is. Similarly, to put max of L plus 1 zeros into memory, well, that's approximately K2 times max of L for some K2. So, okay. What about this part? So here we're saying for E and L counts E plus equals 1. So that is what it looks like. It's a loop that repeats length of L times. So that part takes K3, again, for some K3, whatever is the number of operations for one iteration here, times length of L. So what about here? So here, this is a genuinely tricky part because here it's really difficult to say. This line does not take the same amount of time, the same amount of operations every time, because if you need to put a lot of copies of num into memory, that takes longer. So we can't just say, oh, that's just proportional to the length of counts. No, it's not. Right? So how do we deal with it? So the trick here is to say the total amount of time that line 38 takes over the entire computation is proportional to length of L. And why is that? Well, because in total, it involves putting length of L elements into memory, right? So for each element, in the result, we say put counts nums into memory. How many elements do we put in total? Well, the length of res, which is the length of L. So in total, this part takes up time that's proportional to the length of L. So that would be K4 times length of L operations. Now, also this part takes time that's proportional to length of counts. Right? So length of counts is, again, just length of L. max of L actually. So this part, just this loop to complete it, well, length of counts is max of L. So that's K5 times max of L. So that means that the total amount of operations is K1. So just collect the terms. So this is K1, this is K3. This is K4 times length of L plus, so what's left, K2 plus K5 times max of L, approximately. All right. So here, there's not really best case, worst case. It's kind of the same every time. So what's the runtime here in big O notation? Well, there's nothing you can do. You could just say O of length of L plus max of L. So here you might say, like, how did we get here? You might just say, well, we dropped the constants the way we always drop the constants. That's not quite accurate. So the way you would say it is this thing is just smaller or equal than K1 plus K2 plus K3 plus K4 plus K5 times max of L plus length of L. And for that reason, you get to drop the multiplicative constant. Right? So it's just that we have this estimate for what's the total number of operations. And this is, so then we just upper bound it with this. And then once you've upper bounded it with this, that's the usual thing where you get to drop the multiplicative constant. So the reason that here I dropped down again to doing operation counting is because it's not obvious what else you can do, right? Because you can't just say O of length of L plus O of max of L. That would just not always work. The reason this would not always work, so this is just like as a counter example. So if you do something like for I in range M, and then you do for J in range like whatever M over 2 times M, you can't just say, well, this is like O of M. Like this is actually like M over 2 times M. So you can do it if you, so like the reason this example doesn't completely make sense is that this is something that wouldn't work. What I'm saying is you can't just say, oh, like this is O of M for a set M. It's not really, it's like M over 2 times M. So you can't just say, oh, I'm just doing this M and then I'm multiplying it by this M. You can, in principle, in every particular case, figure out what the answer is, but that's like not reliable. So here, in order to really prove what's going on, I would need to do this kind of operation counting. But again, I did it to the extent that it was necessary. So I just said, I don't care what K1 is, what K2 is, because at the end in my analysis, I was just able to say, okay, like it's all just small equal than this sum of K's, which is constant, times the things that actually vary. Yeah. No, I mean, I was trying to make kind of a straw man kind of example where I was saying, well, you can't just say this is O of M without like also noticing that this is variable. where? Like this one? This is O(m) cubed. Yeah. Right. So since I wrote it down, so I was saying like you shouldn't do it, right? So what this is this goes on for m squared over 2 iterations, and then you repeat that m times. So that's m cubed over 2 iterations. So that's O of m cubed, assuming, of course, that this part is constant. Make sense? So, all right, so you can do that. So this kind of counting sort thing is like it's sometimes useful. Obviously, if max of L could be extremely large, then this could be extremely slow, right? So you could imagine that the integers in the list get really, really large, and there's just not space in memory even in order to store all the zeros. So it can be quite memory inefficient. On the other hand, if you know that there is a set amount which the entries in your list will not be larger than, then it can be pretty efficient. All right. What's going on here? So there was one quiz that didn't show up. You'll get that. So it wasn't quiz 1. So like anywhere where anyone submitted anything, they'll get the credit for the quiz. All right. We're sorry for the technical difficulties. Why is my screen sharing paused? All right. Okay. What did people say for quiz 8? Let's see. Wait, do we have statistics here, or like did they break it? Okay. Yeah, let's see. Yeah, if they broke the interface again and they can't look it up, then we're gonna do the stretching regardless of democracy. Okay, no rubric. Yeah, sorry. They like I think they have like 2 different things, and they for how it happens, and they also keep breaking it. Okay. We're doing stretching if you want. If you don't want the stretching, you can have it. All right. What do we first? Okay. The data was like much better in the beginning of the semester. All right, good stretching. You want more? Yeah. All right. Thank you. Yeah, I'll try to figure out what people said, but I know they keep changing the interface. So all right, so that's like that. So in the interest of time, so I'll show you the dictionary. So for integers, you kind of need to do the list, right? Because if you use a dictionary, then you can't do this part, right? So here I just had for num in range length counts, and I knew that first I'm looking at the zeros, then at the ones, then at the twos, then at threes, and so on. So that's where I put in the order of the integers. So for strings and stuff, you can do a version of this with dictionaries, but I see that we are running out of time today, so we'll do that one on Friday maybe. Now I'm gonna do a different sorting algorithm just to show you kind of different kinds of complexities. So what you're gonna do is called bubble sort. And the idea is like this. So let's say that you start with a list that looks kind of like this. And then here's what we're gonna do. So I'm gonna say, compare this and this, and if they're out of order, then switch. If they're not out of order, then keep them the same. So those ones are out of order. So we'll exchange them. And then we'll check, are those out of order? No, they're not out of order, so we keep them the same. Are those out of order? Yes, they are. So next time we'll switch them. So this is 4 and this is 20. Are the 20 and 2 out of order? Yes, they are. So we'll switch them. Are the 20 and 20 out of order? Well, depends on how you look at it. Either way, whether you switch them or not, it's gonna look the same. Are the 20 and minus 20 out of order? Yes, they are. So next time we'll switch. So you do it the once. And then you do it again. So are the 2 and 10 out of order? No, they're not. Are the 10 and 4 out of order? Yes, they are. So next time we'll switch. So this is 4 and this is 10. For the 10 and 2 out of order, yes, they are. So next time we switch. And so on. So the reason this is called bubble sort is that it's kind of like the larger element bubbles up to the end of the list, right? So that's the idea. So like the 10 keeps bubbling up until we encounter the 20. And then the 10 stays in place. And now the 20, because it's actually the largest element, it keeps bubbling up. So like the 20 goes from here and then to here and then to here and then to here and then to here. So that's kind of the idea. All right. So, or like that's the metaphor. And then the way it's kind of operationalized is you just keep comparing neighbors and say, are they out of order? If they're out of order, then switch. Okay. And the idea is, well, like you keep doing it, eventually nothing is going to be out of order. If nothing is out of order, then the list is sorted. So, okay, let's write that. So I'm going to say, okay, so for I in range length of L, I'll fix it up a little bit later. I'll say, okay, so if the neighbors are out of order, I'll switch them. So what does it mean for the neighbors to be out of order? Well, if L at I plus 1 is smaller than L at I when it really should be larger, then I'll switch. Like so. So one quick way in which this needs to be fixed up is I only get to go up to length of L minus 2 over here because the last time I'm doing I plus 1 and this cannot be more than length of L minus 1. Right, so for that reason, there is a minus 1 here. So the other thing is you do it once, it doesn't make the list sorted, right? So you do it once, what it looks like is this. That's not sorted. However, you do it once, that guarantees that the largest element is at the end of the list. And that's just because, well, it's got to bubble up to the top, right? So like what happened here is like 10 was bubbling up, and then it encountered the 20, and then the 20 is going to keep bubbling up. So like you exchange it with something, and it's still larger than the neighbor to the right because it's the largest element. So that means that I'll keep exchanging it, and it'll keep bubbling up if it's the largest element. If it encounters something larger, which it won't because it's the largest by assumption, then that is going to keep bubbling up. So that means that the first time I do this, the largest element is going to bubble up to the top. And then the second time I do this from the beginning, well, the second largest element can now bubble up to the top because like you could just imagine that the largest one went away, and now you're looking for like the largest, excluding the one that went away. Right, so the second time you do it, the second largest is going to bubble up to the top. You do it n times, everything is going to be in place for sure. So that suggests that we can just do this n times. And if we repeat this procedure n times, well, the first time the last element is at the top, and then the second time the last element is at the top, and also the second to last, and so on. And we have n elements in total. So after n iterations, length of L iterations, we're going to definitely be done. So in fact, you can make it kind of nicer, right? So here I say I in range length of L minus 1. So I keep trying to swap up until the end of the list. But actually, after the first iteration, so after I've done it the once, I know that I don't need to compare anything to the last element anymore because the last element is definitely the largest. And the second time, I don't need to look at the second to last element either because now it's also the second largest. So what I'll do here is I'll say, rather than go up to length of L minus 1, I'll go up to length of L minus 1 minus j. So the first time it's going to be length of L minus 1, and then the second time it's going to be length of L minus 2 because the largest element is already at the end. So effectively, I'm just looking at this list, right? And then the next time I'm just going to look at fewer elements and so on. So that's one thing that I can do. The other thing that I can do is I can say, okay, so actually, if I went through this process and I've never swapped, that means the list is sorted. That's the question from a midterm, right? Because like if I went through the entire list and I tried swapping neighbors and I never swapped neighbors, the list is sorted. There's no point in doing more iterations. So I'll set up a little variable. I'll name it swapped. And it's going to be false initially. And anytime I swap, I say swapped is true. And then here, if I never said swapped true, then swapped is still false. So if not swapped, I'm done. I'll just return. So here note that so this is called sort in place. Right, so if you remember, it's kind of like this. And that's just because it's more convenient in this case to do it like that. Whereas before for counting sort, it wasn't convenient to do that. So we didn't. All right. So that's the whole idea. So now what's the complexity analysis for this? Well, so here it kind of is what it looks like, which is it's a nested loop and it's O of n squared at the end. But actually, you need an analysis in order to do that because there is like lots of things going on. So what's happening here? Well, this is constant time, right? So there's nothing weird going on here. There's like a comparison, and then maybe we swap, maybe we don't. And then here we repeat this thing this many times. Right? So this takes k times. And the reason I say at most is because you would say, well, like sometimes you swap, sometimes you don't. So if you swap more, it takes more time. But at most, it's this much. And then in the worst case, we don't return early. So we take length of L times, so here it's like this, but you can do times, right? Because the J keeps changing, right? So what is it? So it's K times length of L minus 1 minus 0, and then plus this minus 1 minus 1 minus 2, and eventually it's just 0. So the K you can factor out. And there is a length of L every time. And then here, in fact, length of L minus 1. And then here, it's like minus 0, minus 1, minus 2, and so on. Right? Up to length of L. So at this point, we need to and this, of course, so this is length of L, and then this is like length of L times, right? So the length of L here is because it's like length of L plus length of L plus length of L, and we go from minus 0 to minus 1 to minus 2 and so on to length of L minus length of L. So approximately length of L times. And then here we have what's called an arithmetic progression. So that's just the formula. So if you don't know, that's a formula. Still basic. So we'll come back to this on Friday, but the upshot is that this is length of L squared approximately, and this is approximately the length of L squared over 2. So in all, it turns out to be length of L squared. So come back on Friday, we'll finish this. All right, I'll see you. Thanks. Bye.